Section 6.1 and 6.2 cover the states of matter and the energy that correlates with those states. These are your main states of matter. You have solid, liquid, and gas. Solids have a defined shape and a defined volume. They're definitely moving, unless you're at absolute zero, which we have not achieved yet. But as you add energy to them, as you heat them up, they start to move more. And eventually they free themselves of the bonds between each other and they will become a liquid. And that liquid will move. And as you increase the energy of them, it'll eventually turn those molecules into a gas. But the liquid, they have a defined volume, but not a defined shape. Whereas a gas has neither a defined shape or a defined volume. And that's kind of what makes defining things such as slime so tricky, because you might be like, ooh, but it does have a defined volume, but it does not have a defined shape. So that gets it classified, I think, as a liquid, because if you allow it to just run around on your fingers, it's going to take up whatever shape is around it. It may be outgassing some stuff, but if you leave it out, it'll eventually turn into a solid. So sometimes the stuff is kind of fluid, just like the slime. Alright, this graph shows you what happens as you either freeze or cool, as you either heat or freeze an object. And so with freezing, you are removing energy. So if you go this bottom half of the graph, those are our removing energy, whereas the top part is showing you what happens when you add in energy. So the solid will start warming, and then it'll melt and rearrange its structure, and then it'll start warming, and then it'll turn into a gas, and then it'll start heating more. So all of that is adding energy into the system. But what's happening in melting, if you notice, there's no change in temperature at this point, and that's because all it's happening is all that energy is going into rearranging the intermolecular forces, the forces between these atoms, and allowing it to eventually have so much energy that it turns into a liquid. So this is really all that energy that you're pumping into it is used to change the state of matter of the compound. Same thing here. All that energy is just being used to cause it to break free of the surface of the liquid and turn into a gas. But then these up and downs, all that is using energy to either heat or cool an object. If you think about what happens when you put a pot of water on the stove, the temperature is first increased before it starts boiling. The heater, the eye of the stove, first heats that liquid, and then it'll eventually start boiling, but it must reach some point called your boiling point before it will start to boil. Alright, so my question is, what does the periodic table have to do with all of this? Well, it's actually quite a lot. You can look at a compound and kind of predict their relative melting points, boiling points, conductivity, that kind of thing. And how you do it is you just look and you say, hey, is this compound ionic or covalent? And that's going to tell you a lot about those boiling points. So if you look at all of these atoms that are represented here for A, B, C, and D, all of them are nonmetals with one exception, that of sodium. And so that being said, sodium bromide is going to be your only ionic bound compound in this set. And so when you're looking at this, you will know that sodium bromide is going to actually have the highest melting and boiling point, just simply due to the fact that it was the most ionic compound in this bunch. And so why is that? Well, sodium bromide, when you stick it in water, it's going to form ions, which means it's going to really want to interact with its peers, everything around it. Whereas if you stick a nonpolar or just a covalently bound compound into a mixture, it's going to not form as strong as mixtures as sodium and bromine do, because of the fact that it has that +1 charge and that negative charge. So positives and negatives will attract and make them really want to be attracted to each other, which means in order for them to melt or to boil, you have to supply a whole lot of energy to get those negatives and those positives to break apart and allow them to form into a gas. Similarly, which of these solutions would conduct electricity? Same principles apply, that if you throw them into water and it forms charged compounds, it's that charges that actually allow the movement of electrons from one species to another. And then the last question is very similar once again, but I wanted to give you one more to practice. So feel free to think about this, pause the video, but just think, which of these requires the greatest amount of energy to melt? Is it methanol, sugar, potassium chloride, or hydrogen sulfide? I hope you said it was KCl because that is the only ionic compound in this group, and notice everything else would be covalently bound, but potassium is the only metal in this section. All right, now go read section 6.3 and 6.4.